Alright, link reaction. This is the one a lot of people seem to mess up on or forget about. So a link reaction is joining up glycolysis to Krebs cycle. It will occur inside of the mitochondria, in the matrix, the mitochondria. So if you remember, we finished glycolysis and we had pyruvate, which was this 3-carbon compound. Now, it's, I think, important here to remember that every step we do in the link reaction, and in fact in Krebs cycle, is doubled up, because we ended up with 2 molecules of pyruvate at the end of glycolysis. It's just that we deal with each molecule separately, so keep that in mind. They will like to ask you questions, and be careful, look at what it says. If it says how many molecules, for example, of ATP are generated in the Krebs cycle per molecule of pyruvate, then you need to think of it in single terms. If it said how many molecules of ATP per molecule of glucose, you would have to double it up, because it's split into 2 things as it comes on. But we'll deal with the Krebs cycle later on. So we've got our 3-carbon compound. Now the first step that goes on, again, we've got another enzyme control step. Remember, this is what the arrow means, it's an enzyme control step. We converted pyruvate into acetyl, which is a 2-carbon compound. Now, a couple of steps going on here. We are going from 3 to a 2-carbon compound. I'll talk about acetyl in a second. That must mean we have removed a carbon. Now, carbon doesn't just pop off on its own. It comes up in the form of CO2. This is called decarboxylation. And we can even put in the name of an enzyme here. Let's call it decarboxylase, because that's the enzyme. Remember, here's a good word to use as well in your answers. It's decarboxylation, removal of the carbon, the carboxyl group, sorry, from our molecule. Now, if we've gone from 3 carbons down to 2, remember, a carbon has got these 4 bonds. I don't know, it balances out with CO2, but if you think of a pyruvate molecule, carbons, carbon, carbon, 3 carbons, in effect, whenever we remove a carbon, we're going to get hydrogens lost as well. But of course, they're not lost, they're picked up, and it's picked up by our old friend, the coenzyme NAD. So we get reduced NAD. So that's why we've lost those hydrogens. A carbon's come off, if you like. Remember that a reduced NAD is picking up 2 hydrogens. Oops. Let's pop that in there, worth remembering. So that's what we've got so far. Now, I said I'll come back to acetyl later on, because there's another little step I want to just show you. The acetyl is picked up by another coenzyme, and this is called Coenzyme A. And it's written in your books like this, acetyl coenzyme A. You may well see it written like this as well. ACOA. Make sure you notice that the C on the coenzyme is a capital there. And that's fine as well. So acetyl coenzyme A. What's the purpose of this coenzyme A? It's there, if you like, to shuttle this molecule. That's the important bit, the acetyl, to get it into the Krebs cycle. And without it, the acetyl wouldn't be able to get in. In fact, as it's released, it forms this molecule, acetate, which is a 2-carbon compound. I'll come back to that in a second, where this has come from. The coenzyme A is released, and it will then recycle around. It will go up and pick up some more, so we can get some more pyruvate come into the system. So the coenzyme A is just cycling around. It's there to get this into the Krebs cycle. Okay. And that is the link reaction. If I just hide those for a second. Pyruvate to acetyl, coenzyme A to acetate, and we've got the coenzyme A cycling around. Do remember these steps, the carbon dioxide, the reduced NAD, those are the ones that people will tend to get wrong. Okay, I'll just mention this acetyl. Again, this isn't necessary for your syllabus, but I think it's useful because you get an idea of where things are coming from. If I draw, this is a molecule of acetyl. Okay, so rather than doing an empirical formula, There's the structure of it. Now here we could have, it could be any particular, could be an atom, could be a particular group. Look at it here, CH3C double bond O. So for example, if we look at another, I'll just redraw this in a kind of straight form. Okay, that should be a familiar molecule to you. We've got the carboxyl group. Okay, COOH. That's as it's written out. That's the same molecule, which is ethanoic acid. Okay, the carboxylic acid, ethanoic acid. It's just that without that functional group on there, that bit is referred to as acetyl. Now, if we go back to our pyruvate, if you watch the one on the video on glycolysis, and we worked out that pyruvate, and I'll just draw the empirical formula here, was that. Okay, the empirical formula for our acetyl was C2H3O and then whatever else we have. So for example, if it was ethanoic acid, we'd have that group would be on the end. That would be the functional group. Okay, it's not such a big jump to get from one to the other. You might say, oh, well, they're different. Yeah, we've lost one carbon, different. We've lost, if that was acetyl, we'd lost 2 oxygens. Well, that's what happened in the link reaction up here, isn't it? We lost a carbon and 2 oxygens. So it's not actually such a big difference at all. So that's the acetyl group. I'll put the OH on there to show you the end, but that's the acetyl group. Okay, the only difference between that and the pyruvate, as we did it on the pyruvic acid, is we've lost a carbon, 2 oxygens. I know we've got another hydrogen, but that's because of the way I've drawn this. Okay, so I just want to show you how those are related. In fact, what happens with the coenzyme A would be joining onto here. It joins it by using a sulfur. It's a thiol group, and the coenzyme A is a bigger molecule that sort of sits on here, but that's where it joins on. Now, if we then look at the acetate, which is where it goes actually into the Krebs cycle. If I draw acetate for you, here it is in the kind of structural version of it. You can see that actually it's just this acetyl group, except we've got an O minus on it. It's this with the end knocked off, if you like. So in fact, you'll also find that that's sometimes called, and if you followed the working of this, remember that was acetic acid. If you get rid of that so it becomes ionized, it would be acetate. In the same way, if we called it ethanoic acid, we can now refer to that ion as ethanoate. That's the difference between lactic and lactate, and pyruvic acid and pyruvate, and citric acid and citrate. It's just that it's the ionized form. Okay. Hopefully that's added to it and helped rather than confused you, but I think that's useful to see, certainly for the chemists, where these things come from. If you're not interested in the chemistry bit, just remember that bit.